Okay, welcome, and let's get started. Very glad to have Dr. Dave Fritts today from GATS to give a colloquium. Here's some information or data from Dave. Dave received his PhD in physics from the University of Illinois, and actually I didn't know he worked at NCAR afterwards for 2 years as a postdoc. And then Noah. That's right. And ASP, I guess. ASP postdoc. Yeah. And after that, he joined the physical dynamics at Washington State as a research scientist. Then he went further north, way north this time, to University of Alaska, and spent 10 years there as a professor in the Geophysical Institute. He then came back to Colorado. From 91 to 97, he was a research professor at the Electrical Engineering Department at CU, where he's still a adjunct faculty. And in 97, he founded the Colorado Research Associate, which is a branch of the Northwest Research Associates. And more recently, he founded GATS Boulder, where he's also the manager. Dave is, of course, internationally known for his original and very prolific research in the area of gravity waves, instabilities, and turbulence, and using very novel observational, theoretical, and numerical methods. I remember the first research paper I was given when I was a graduate student in Michigan was Dave's 1984 review paper. I was just feel overwhelmed and almost gave up at that time. Huh? No, it's an 84 paper, but I read it in 91. So a little bit behind. So today Dave is going to discuss the very exciting and new DEEPWAVE results.
Thanks greatly, Hanley. So can everybody hear me with this walkabout mic? Does that work? Well, thank you, first of all, for everybody coming today. I don't know how many of you know the history of deep wave planning, but the PIs that are listed here spent a large chunk of a decade trying to sell this program to NSF and to the community, and then ultimately making it happen. So it's very exciting for me today to be able to be the first to describe these in public after 6 years of efforts trying to make it happen. For a long, long time, we would go to meetings talking about the deep wave program that would be coming along, that would give us great results and which would have really spectacular instrument capabilities. But none of that had come to fruition until today. So what I want to do today is, first of all, acknowledge all the people that have helped us make this happen. The PIs are myself and Ron Smith at Yale, Mike Taylor at Utah State, Jim Doyle and Steve Eckerman at the Naval Research Lab, and Steve Smith at the Boston University. We have lots and lots of co-Is who have helped make this happen. Biff Williams, in particular at GATS, where's Biff? Back here, was instrumental in building some of the key new laser capabilities that we now have installed on the G5. Dominique Paté, working with Mike Taylor at Utah State, was instrumental in the imaging capabilities that were also developed for this. And then we have lots of colleagues in Germany at DLR and at the Australian Antarctic Division in Australia who built specific instruments to enhance our potential capabilities for deep wave measurements. We benefited from a long involvement with a very large and accomplished team at EOL here at NCAR. They helped us with flight planning, assessments of places where we could go, integration of the instruments, and so on. And we had many additional colleagues and students from our teams and others who helped us make these field measurements possible. So I think altogether we had something like 60 people participating with us in the field over the course of the 6-week experiment. So the motivations for deep wave. Why do we care about deep waves in the atmosphere? Well, we know now pretty well that gravity waves account for the primary vertical transport of momentum from the lower atmosphere throughout the MLT. The important scales oftentimes are not resolved by the larger scale models that we attempt to use or by the satellite instruments that we use to try to constrain those models. This implies that we need gravity wave parameterizations, and the existing parameterizations are known to be deficient in a number of important respects. So a key goal is to try to improve these parameterizations. We believe this requires a much improved understanding and coordinated measurements and modeling. And so that basically was the motivation for our program from the start. So just to give you a context, this is a map of the gravity wave scales that are probably reasonably relevant in the atmosphere. This rounded rectangle at upper left shows the range of horizontal and vertical wavelengths that we think likely contribute most to gravity wave momentum fluxes throughout the atmosphere. The yellow region here, the green region here, and the pink region here show the anticipated resolution capabilities for the various microwave and infrared limb and sublimb sounders and current GCMs. The gray area here suggests the potential measurement capabilities for in situ and ground-based measurements. And the blue dashed rectangle shows what we are trying to achieve with our deep wave measurements. What's important to note here is that most of the other global measurement capabilities fail to resolve an awful lot of the important scales that we believe contribute very significantly to the fluxes of momentum in the atmosphere due to gravity waves. So our approach with deep wave has been to perform comprehensive measurements in a region that provides really good sensitivity to some of the more frequent and more common sources that occur throughout the planet. We chose this region, though, because it also provides other benefits that I'll talk about shortly. We chose to expand the gravity wave measurement capabilities aboard the G5 by adding these new measurements that I'll talk about to extend measurement capabilities from the surface to 100 kilometers. We chose to try to expand our deep wave team funded by NSF to include a number of other US colleagues and international participants. And we also chose to include very extensive forecasting and modeling activities to assist us with flight planning and to try to aid us in improved understanding of the measurements once they arise. Well, 6 years ago, the initial target for this program, which at that time was named Sangria, was the Southern Andes and the Antarctic Peninsula. But that was judged to not be feasible for lack of an adequate hangar space for the G5 early on. And so 2 years ago, we made sort of a command decision with the EOL folks and with NSF. NSF said, well, you either need to cancel this project or you need to delay it another year. Had we delayed it a year, we would have lost our NRL colleagues. And so we said, well, we don't really have to go here. We could slide it a bit in longitude because we know you guys have experience operating out of Christchurch. And so during that telecon, NSF agreed and NCAR agreed that they could support a renamed program out of Christchurch. So that's how DeepWave arose. So DeepWave is now targeted not the largest southern hemisphere gravity wave hotspot, but it was the second largest, and it had a lot of other things going for it. It had strong topographic sources that are illustrated by these errors. They had averaged over 8 years. It had significant winds across the southern island of New Zealand. These are statistics for July, average for 20 years, or shown for 20 years, and the mean shows that there are about 14 or 15 events that achieve a nominal threshold for wind speeds that are believed to excite mountain waves that readily propagate to much higher altitudes. And this was confirmed by our deep wave measurements, where we saw in a 6-week observing period about 20 such events. So the statistics predicted here bore out, and we were able to get a number of really good cross-mountain flow forcing cases. Additional good evidence came from the errors measurements that were analyzed by Steve Eckerman in advance of this program. These show errors retrievals showing anticipated temperature perturbations at 2 hectopascals, or about 41 kilometers. And these show examples on the left that suggest mountain wave responses and strong trailing waves in a couple of cases. Other events where there were strong wave responses to something that appeared not to be terrain related, and other cases where there were apparently multiple sources acting to excite this large amplitude wave field at about 41 kilometers. So a lot of evidence suggested that this would be a good site for these measurements. One additional factor that was a big advantage in going to the southern hemisphere was we had the potential for a stronger jet structure, a zonal wind structure, that allowed whatever amount of waves might arise at lower altitudes to more readily propagate to much higher altitudes. We also, by going to the southern hemisphere, much reduced the potential risk of a sudden stratospheric warming intruding on our measurements, which we'd had happen to us in a rocket campaign in northern Norway quite some years ago. So the notion was that we would base the aircraft here at Christchurch. We'd have the potential to fly legs exploring terrain, forcing over Tasmania, over New Zealand. We could probe with predictability flights, the Tasman Sea, and then we could look to other sources of waves to the east and south of New Zealand and in the southern Tasman Sea as well. And for this purpose, we used both the G5 at NCAR that was configured with 2 new LiDARs and a new AMTM, an advanced mesosphere temperature mapper. And about 2 years before the campaign took effect, we were able to persuade our German colleagues at DLR to join us, and they brought their Falcon research aircraft to join us for the last 3 weeks of the campaign. So this is an example of the data that has come from our LiDARs that Biff built. This is Biff standing inside the telescope on the airplane. He built a UV laser that basically is a pulsed system. It basically gets us Rayleigh returns, so we're able to measure densities and infer temperatures from about 20 to 60 kilometers. And this is an example of 4 South Island cross sections with that system, measuring from 20 to 60 kilometers. The hot spots here at higher altitudes are not lack of data. Those are regions where the temperature is saturated. So in general, we get very good data with a relatively short integration period that extends from 20 kilometers to 60 kilometers. And the sodium LiDAR that Biff also built and somehow managed to squeeze into 2 standard G5 racks measures sodium densities and inferred temperatures from nominally 80 to 100 kilometers, but oftentimes in this experiment, the sodium layer was found to extend to much lower altitudes. In some cases, these measurements went down as low as 72 kilometers and as high as about 105. So the 2 LiDARs together span a very large fraction of altitudes between 20 and 100 kilometers above the aircraft. At the same time, Mike Taylor and Dominique at Utah State developed a new version, an aircraft version of their AMTM. And this was designed to look vertically from the aircraft, and it was designed to look both along track and cross track. This is an example of a time series of those measurements shown in brightness rather than temperature. This track corresponds to the along track and cross track field of view of the AMTM aboard the plane. This is the camera looking up. It has a kind of a skewed view because it's looking out of a slanted port, so it can't quite get as large a cross track sensitivity as it would like. And then Mike very cleverly, at the last minute, talked the EOL crew into allowing him to put on 2 small wing cameras as well, looking out each side of the camera, each side of the aircraft. And so those were slanted up to look at the ergo layer. And the combination of the side viewing wing cameras and the overhead view combined to give us an approximate 900 kilometer cross-track swath of fine structure at 87 kilometers altitude wherever the plane flew. And this is an example of the along track temperature perturbations that correspond to this brightness variation here in the center. So with the LiDARs measuring almost a complete vertical profile along track, and the imagers measuring the response at large and small scales spanning a 900 kilometer cross-track field of view in the mesosphere, we had some very formidable capabilities aboard this aircraft for the first time. I'm sorry, that's the OH ergo layer. So it's an ergo emission that he's monitoring. And so the temperature comes only from that region. So in addition to improving the instrumentation for the G5, in order to make it relevant to deep gravity wave propagation, we also greatly enhanced the ground-based measurement capabilities in New Zealand. This is a list of the instruments that were added. The EOL crew brought the NCAR ISS, which had the 449 megahertz boundary layer radar and balloons. At Hokitika, we had additional balloons from NCAR and at DLR. At other sites, we had ergo imaging from Steve Smith at Boston University, at Mount John, and at Lauder. Mike's installed a second MTM on the ground at Lauder. And then we also had Rayleigh LiDARs at Lauder and with our Australian colleagues in Tasmania as well. So we had an enormous complement of ground-based instruments to support the aircraft measurements at higher altitudes. So if I put all this together from about 40 south to 60 south, which is the range of latitudes that we sampled with these different instruments, the DLR and its down-looking LiDAR measured essentially at flight level and below the aircraft. The G5 measured in situ around the airplane from about 80 to 20 kilometers with the MTP. Both of the aircraft had drop-sons to the ground. And the GV also hosted our sodium LiDAR, which measured in the lower stratosphere, and again between about 70, 75, and 100 kilometers at higher altitudes. The Rayleigh LiDAR, which measured from about 20 to 60 kilometers, and again the AMTM, which measured at this very narrow layer at 87 kilometers, allowing us to image the wave structures that got to high altitudes. We also implemented a large number of forecasting tools in the field with us to assist with flight planning. We use the ECMWF IFS, the NCEP GFS, the NOGAPS Alpha model, and COAMPS, NIWA, and WRF models, all for forecasting tasks in the field. All these data sets were available to us in real time in the field in Christchurch. And then we're anticipating also using a number of these, as well as our own GATS, very high resolution models for deep gravity wave propagation to assist us with the analysis of the results as they evolve. So this is a plot that's put together by Andreas. This is a sampling of the ECMWF IFS model throughout the entire campaign period, and it shows the occurrence of the different IOPs hosting the different individual flights that we managed. And it shows the correlations of the IOPs with the enhanced lower level winds throughout the entire campaign. Now, each of these IOPs had anywhere from 1 to 3 different research flights. So altogether, the G5 flew 26 research flights, and the German Falcon flew 13 research flights during this time period. So this is a bit of a complicated plot. This is from Ron and his group at Yale. The upper plot here shows the estimates of vertical energy flux for individual flight legs for all the cross-mountain flight segments. So basically, each of these vertical profiles shows Flight 5, for example, Research Flight 5, Research Flight 12, Research Flight 16. And within each of those are a number of individual cross-mountain segments, and each dot represents the average vertical energy flux for that segment. And you'll see that some of them are very close to zero when the forcing was quite small. Some of them are quite large. These represent the stronger anticipated forcing events. And the lower panel here shows the corresponding estimated energy fluxes from the Yale version of the WRF model at 6-kilometer resolution. And you see a close correspondence between the strong responses seen in the data and the strong responses anticipated from the model at lower levels. So the models in this case seem to do quite a good job of anticipating the responses at higher altitudes. And this is very, very different from what we experienced during the MAP campaign in Innsbruck in 1999, when the models were much coarser and when the terrain was easy for the air to go around rather than over. So what I'm showing here also are highlights of a couple of the flights that I'm going to show some results from. These include RF7, which is an interesting flight in its own right, but not a strong mountain wave flight. These two strong mountain wave flights, another case where we had mountain wave segments built in, but we intentionally targeted a very weak forcing condition. And then a couple of other research flights that looked at other sources over the Southern Ocean. And finally, one event, which I label here no research flight, where we had very, very strong forcing in the MLT, strong responses in the MLT, despite the fact that the forecasts were for very, very weak forcing at lower altitudes, which caused us to choose not to fly at all. Now, yeah, it's interesting to look at. Typically what you see here is that the highest values of the energy fluxes that are seen coincide with the model values. So the energy fluxes are typically smaller than the predicted values at flight level. And what is really interesting is, in some cases, I mean, the energy flux is an indication typically of whether the waves are going up or down. If the energy flux is positive, the waves should be going up. So if the energy flux is negative, that doesn't mean that it's a bad result. It means that because of the nonlinear dynamics that are probably occurring at flight level or in the lower stratosphere, for that interval, the dominant flux may have been actually going downward, maybe due to secondary gravity wave generation. So there is a lot that we're going to need to work hard to diagnose here, and the model probably does a more linear job of estimating the energy fluxes than we actually see in the atmosphere because of its limited resolution. Well, my sense is that what we really ought to be doing here is not looking at a segment averaged energy flux, but looking at the energy flux averaged over the wave scale instead. I'd rather develop a local perspective and a local understanding of what the wave field is doing across the island rather than just taking a large average. Yeah, definitely can. Yes. You want to average enough to make it make sense. I'm not sure you want to average over many, many different portions of the wave field. Done. U prime, no, energy flux is W prime P prime. And you can also get it via the Elias and Palmer relations from the momentum flux as well. But this is all a preface. Let me get to the interesting results. Okay, so let me talk first about RF07. This is a case where the meteorology suggested that there might be a number of interesting sources. We had basically a low-level flow from the southwest. So the predictions were for vertical velocities that had phase fronts kind of normal to the incident wind. The forecast also suggested that we had a very low tropopause height here, a strong frontal zone here that was moving towards the northeast, and the cross-mountain flow, or the along mountain flow, suggested that we ought to also be having strong trailing wave responses at higher altitudes. And this is a horizontal cross-section at 2 hectopascals, or about 41 kilometers. And this is a vertical cross-section, I think in an east-west direction at that position. And it again suggests that these trailing waves have the potential to penetrate to quite high altitudes, arising from relatively weak flow over the terrain. So with very weak forcing, what should we expect to see? Based upon that forecast, we designed a flight path that was kind of convoluted. We took off from Christchurch, flew southwest along the spine of the South Island to the east, and then we flew a full, well, 3/4 of the way around that rectangle. We did another round trip there and then returned to Christchurch. And we chose that flight path because it appeared nicely to capture a potential wave field at 41 kilometers that was anticipated by the AIRS data somewhat prior to the flight. And so I'm just going to highlight a couple of different altitude responses here. These are a long track plots of the long track velocity U prime and the vertical velocity at flight altitude. And one sees a nice clear response here at larger scales that correspond probably to the frontal waves that are behind us. We're flying, remember, from WP5 to WP6 along this segment. And then there was significant convection below the aircraft here, and we see strong responses in that region as well. And all throughout that activity, we saw some responses at smaller amplitudes accompanying these larger perturbations, but a lot of very high frequency stuff that almost certainly was trapped waves that cannot be resolved by the models, and which probably does not contribute much to the total energy flux. So that's kind of the chaff from which we need to try to identify the signal. So what was really remarkable in this case, especially given the unusual and long and varied sources, was the agreement between the observed LiDAR measurements, this is shown in the colored portion here, overlaid with the phase structure for the predicted temperature perturbations by the ECMWF model interpolated in time and space to the aircraft position. So again, the contours are what ECMWF tells us we should have seen based upon their 16-kilometer global model along the flight track for this entire flight duration. And the colored contours here show what we actually saw with the LiDAR between 20 and 60 kilometers. And I think the agreement is absolutely phenomenal. The phase structures do not always align exactly, but what does seem to line up really well are the the tilts with height, the refraction of the waves as they propagate vertically, and the horizontal scales that are anticipated by the large-scale model despite its relatively coarse resolution. Biff, discontinuity at 40? Han Lee was asking if there is a discontinuity in the data at 40. Okay, so you have a longer average in time here at higher altitudes. Yes, okay. So moving to higher altitudes yet again, this is the AMTM at 87 kilometers, and this is the early part of the flight track. Essentially, this is a kilogram. This is basically a cross-track pixel line from the center of that imager mapped in time along the flight track. And so you can see as we flew south, it has a lot of structure here, which seems to have phase structures aligned sort of in a northwest-southeast direction as we had anticipated for the mountain waves. As we turned this corner and headed east, we saw wing camera off to the right, circular wave patterns that seem to coincide with convective activity off the west coast of New Zealand. As we turned north, we saw as we headed toward the front, which was in this region, and propagating or moving towards the northeast, we saw significant waves which, looking at the correlations of velocities at flight level, appeared to be propagating from the front back to the southwest. And then when we turned the corner here at the northeast corner, this is somewhere we crossed the date line up here, and the software on the plane thought we had flown all the way around the planet and gotten back to it from the other side. But nevertheless, the plane didn't seem to be lost, and we managed to get back down here over this convection before turning and heading for home. And as we were over the convection, we saw relatively rapid, small-scale responses to that convection at 87 kilometers. So it appeared in this case that the AMTM provided persuasive evidence that a lot of these sources, despite their having relatively weak forcing at lower altitudes, have a ready potential to propagate gravity waves to very high altitudes very quickly. Okay, let me turn now to Research Flight 12. This was part of a pair of flights. This one had relatively strong forcing, but very restricted penetration. You can see that because this is now the WRF model that was used for aid in these forecasts. We saw very strong anticipated vertical velocity responses at an earlier and later time. These are separated by 3 hours. But that response was confined to below about 200 or 300 millibars. And then thereafter, because of a much weakening stratospheric flow, it was anticipated that those waves would dissipate quickly in the stratosphere and not get to much higher altitudes. So based upon that, we designed a flight plan that would allow us to do rectangular cross-mountain circuits over both Mount Aspiring and Mount Cook, the two most prominent mountain features on the South Island, and I'll show you some of those results. So again, we were able to do multiple circuits around that rectangle. All of the red highlighted areas here are for the upstream or westward flights over Mount Aspiring. The blue are the eastward and downstream flights over Mount Cook. And if you look first at the vertical velocity, you see that there is a significant enhancement in the vertical velocity with some very large spikes over some of these flights. This one in particular was about 8 or 9 meters per second, and after the pilots pulled out of their dive, the pilot came back and said, "Whoa, did you feel that? We dropped 100 meters in about 20 seconds, or 10 seconds or whatever it was. The plane just, boom, it just dropped out of the sky." And so Scotty said, so because of that event, they turned up their nominal Mach number for flight so that they would avoid a stall finding those kinds of events in the future. Because when you go through a wave-breaking event like this, your motion relative to the air can drop very suddenly. So what is also interesting here is if you look at the horizontal velocity, the along track velocity, this is measured relative to zero. Zero means the horizontal velocity of the air relative to the ground. And on each of these flights, when we were headed west, flying over Mount Aspiring, you see as we go to successively higher altitudes, the wave-induced velocity increases from negative values closer and closer to zero. And this last flight, which was at 45,000 feet, found us in an environment where the horizontal velocity along track was identically zero. But that means that the wave at that point had achieved a perturbation velocity upstream that exactly compensated the mean flow, and that meant that we essentially flew right through the wave-breaking region at that altitude. Okay, additional, that was research flight 12. This is research flight 16. This was another case with quite strong forcing at lower altitudes, stronger even than before. But what we see here in the WRF forecast is strong, apparent secondary wave generation. The waves that are going up from below, from the surface, have a preferential westward tilt with altitude. In this region, though, you can see evidence for waves apparently having both an upstream slope toward the west and a downstream slope toward the east. And this is suggestive of strong nonlinearity near a critical level, strong wave breaking, and the likely radiation of secondary gravity waves from that region. And so if I align Biff's LiDAR measurements with the Rayleigh system in the stratosphere with this, the coincident volume is here in yellow in each case. You get some sense of this crossed wave structure down here that you see in the model predictions. But if you follow those to higher altitudes, the crossed structure, the apparent upstream and downstream propagation superposed, become more obvious. And we also see that those waves extend to higher altitudes and grow in amplitude. Another similar feature between these observations is this relatively quiescent region downstream in the lee of the Southern Alps. And we see a similar quiescent region here where we don't have as significant wave activity. So again, it looks like the model did a pretty good job of forecasting what we saw. We have not tried to look at the exact phase alignments in this case because the horizontal structure of the wave field is quite small in the higher resolution WRF predictions. Another interesting aspect of research flight 16 was that the forecast had anticipated a diminishing forcing at the surface, a diminishing cross-mountain flow at lower altitudes. And the upper panels here are, again, from the AMTM at 87 kilometers. This is now from Lauder. The lower forcing had allowed the skies to be clear over Lauder, so our ground-based AMTM was able to get us good results. These are images from that, and the field of view here is 180 by 144 kilometers. These are flights near the tail end of the research flight, and none of these suggest any evidence for stationary waves at these altitudes. But as the forcing diminishes, and after the flight landed, we began to see things that were very, very stationary at higher altitudes. And these are, again, signatures of now reforming mountain waves at higher altitudes because of the weaker lower altitude forcing. When you force very strongly at lower altitudes, you get lots of wave breaking in the stratosphere. The response is very nonlinear, and you break up the primary wave propagation. When the forcing is much weaker, the waves do not become nonlinear in the stratosphere. They can sneak through, they can continue to grow linearly, and they can achieve large stationary wave patterns again in the MLT. So there was almost this anti-correlation between very strong forcing and very strong responses at high altitudes. In just an hour or two if their vertical wavelength is large. So this is another case, RF22, where we had relatively weak forcing. We specifically targeted weak forcing. Now, having learned our lesson, having looked at some of these data and said, wait a minute, it doesn't have to be strong forcing to have really interesting results at high altitudes. So this was a case where we specifically looked at a weak forcing case. The contours, the red contours here that I think you probably can't see really well, show that the lower level winds were quite small, especially near the surface at mountain height. And these were 4 successive legs that we flew east-west, more or less over Christchurch. And they show successive, let's see, that would be a west-to-east flight, an east-to-west, west-to-east, east-to-west, west-to-east flight. And so these are flipped contours because we're first flying upstream and then downstream. What is really interesting here is that, again, the ECMWF model predicts phase structures which align really, really well with what we observe with the LiDAR on the flight in the stratosphere. And they also seem to anticipate the phase structures we see at the bottom side of the sodium layer, where we have very, very large excursions in sodium density displacements. This has almost never seen. We've operated a LiDAR in Norway for a decade or so, Biff, I think. Have you ever seen the sodium get this low? So these are very, very large excursions of these apparent mountain waves extending to 70, 75, 80, 90 kilometers, and they're obviously having very, very large impacts and large vertical displacements at the very highest altitudes. And what's remarkable is the 16-kilometer global ECMWF model captures the structure. So if we look at in more detail at the sodium data at higher altitudes, if we really want to do particle tracking, we have to look at the mixing ratio rather than just the sodium number density. So when we do that and plot the sodium mixing ratio here, we see that there are a whole bunch of places where these surfaces are turning almost vertical, or perhaps even beyond vertical, because the chemistry that accompanies mixing at lower altitudes would rapidly eradicate the neutral sodium atoms. So if something is steep here, it's probably steeper in reality, because this is not an exact tracer. And this suggests both large displacements and potential overturning these waves at these altitudes. Let's see that last one. Okay, so this gives us an additional perspective on these waves at these very high altitudes. Again, this is the OH layer at 87 kilometers. This is one of the cross sections that was flown. It doesn't show the western edge here, unfortunately, but what one does see in the animation I'm going to show you shortly is that you see a bright band here, another bright band here, and a third bright band here, and there is fine scale structure embedded within those bright bands. You'll see in the movie that these fine scale features are indeed propagating or advecting to the east, but the large scale bands are stationary. It turns out that these correspond very nicely These correspond very nicely with the 240-kilometer large-scale wave that I thought I showed. But what you'll see here I think that'll work. There it goes. Okay. So this is the plane maneuvering to do these cross-mountain flights. Now going east to west, then from west to east. So this is the central AMTM aboard the plane. These are the wing cameras again. Sorry if that makes you dizzy. It does me. But you can see that it continues to paint out these large-scale features that are stationary here and further to the west on every successive flight. The large-scale features are not moving, so these coincide closely with what we see with the LiDAR at lower altitudes. They correspond to a 240-kilometer wave length in the horizontal that, interestingly, is aligned with phases normal to the wind direction rather than along the island. You will have seen from some of our earlier flights that the mountain waves seem to have different alignments depending upon the wind direction rather than the terrain. And that is, I think, something that we had not expected. So these very large amplitudes at high altitudes beg the question, how big an effect can these waves have? So we've gone through the exercise of estimating rough momentum fluxes for these waves. And bear in mind that in the MLT, typical values are roughly 5 to 10 meters squared per second squared as an average. That's what is necessary to close the mesospheric jets and reverse the circulation and account for the residual circulation at higher altitudes. So when we put in the appropriate parameters here, we can use the Rayleigh LiDAR 60-kilometer measurements. They suggest a temperature perturbation of 15 K, mean temperature of 250. If you do a flight average, that's the temperature profile extending to 70 kilometers. And then other observed parameters, we get a momentum flux which is about 70 meters squared per second squared, or 7 times 10 to the minus 3 Pascal. If we do the same thing for the dominant mountain wave structure at higher altitudes, and in this case it's an 80-kilometer wave that you saw in the sodium density data that was embedded within the 240-kilometer larger scale wave, and again the suitable parameters, you get an even larger momentum flux at higher altitudes. So again, these are very, very large values compared to the background values we expect in the mean. And this suggests that if there are sufficiently many of these very strong events at these altitudes, they could play a very large role in accounting for the dominant forcing at those altitudes. I think, yeah, this is just... no, well, this is absolute, so it has to be smaller. If I've got wave dissipation occurring between here and here, I expect this one to be smaller. Remember remember the velocities are larger, but the density is a lot smaller. So I multiply by a smaller density, and that's going to reduce the total. So here is another really interesting flight. I wish we had done a second one. This is a case where we elected to go out throughout the entire DeepWave mission. We had looked for opportunities to look for responses to the small Southern Ocean islands under suitable wind conditions. And this is Auckland Island. It has a maximum height of 700 meters, so it's not a big target. Here it is. It's diminutive compared to the terrain of the South Island, but when you get the right forcing conditions here, you might nevertheless expect an interesting response. And so this was a case where we had a flow towards the sort of east-northeast across Auckland Island at about 20 meters per second, I believe, yes, at relatively low altitudes. And what I'm going to show you here is again, the AMTM response and the wind camera response as the plane flew over Auckland Island 4 different times. These are trailing waves, probably. As you get close to the island, you can see a distinct ship wave pattern here. This closely tied to the terrain, quite large in amplitude, quite large in intensity perturbation. And we'll come back and do 3 more passes. Unfortunately, because there was interest in flight level winds, we dipped down for 2 of these and only got LiDAR data for the 1st and 4th passes. So here again, as you come up on the island, you can begin to see nice ship wave patterns that extend out from the central portion, especially up to the north side. There's increasing evidence, strong responses there, but now this wave is breaking up here. It looks like it's going unstable. Oftentimes 40,000 feet. So again here, now you see the wave largely dissipated in the lee of the mountain, although you still see some residual extent to higher latitudes to the north and east. So this seems to be a case where we have strong winds at lower altitudes over a very weak boundary, or a very weak barrier, which nevertheless yields waves that can readily get to very high altitudes and achieve very large amplitudes. And in fact, the fact that we nicely saw this wave going from a more linear state to an apparently unstable state and a broken up state suggests that this wave was breaking at those altitudes. This is a plot that Dominique and Mike put together that also emphasizes the coherence of the wave structure when this vertical viewing camera was immediately in the lee of the island. It suggests that the temperature perturbation was 20 K and that the horizontal wavelength was 40 kilometers. Now, you have to recognize that the temperature perturbation that is inferred from the AMTM is also almost certainly an underestimate of the true perturbation that is there, because it's averaging over a layer that has a full width half maximum of at least 7 kilometers. So if the vertical wavelength of the wave is in any way restricted, the true temperature perturbation must be larger than that by a significant degree. So again, we can estimate the momentum fluxes, and in this case, the value is even larger. It's remarkable that such a small target can potentially have such a big effect at high altitudes. So this is roughly 100 times the background mean, and it means that this tiny little postage stamp of an island projects a much larger response onto a much larger area as well. So it's just like in the stratosphere, where the people doing constant pressure balloon measurements are arguing that the tail of the distribution with very, very large amplitudes is probably accounting for a disproportionately large fraction of the total flux. I think we can make the same argument in the mesosphere. Sorry? No. This is a ship wave. And the different winds that wave pattern encounters as it propagates to higher altitudes filters out portions of that packet. And the only part that we see... No, the vertical wavelength is dictated by the background stratification and wind. So the vertical wavelengths typically that we see in the mesosphere can vary anywhere from about 15 to 30 or 40 kilometers. If they're smaller than 15, we really don't see them very well because they're phase averaged, even if their amplitudes might be significant. So Research Flight 25 is another interesting case. I'm not going to talk much about it, but it's a case where we chose to probe the Southern Ocean to high southern latitudes because of jet structures that seem to be suggesting high altitude responses, again in the ECMWF forecasts. And this again is a comparison of ECMWF contours of temperature with those measured by our Rayleigh LiDAR. And again, the phase structure, especially at higher altitudes, is really, really good. And even including the refraction to higher altitudes because of the changing n squared or wind environments. And in each case, the wave fields seem to point back to a jet stream maximum at lower altitudes. So it's quite fascinating that the models, despite their relatively coarse resolution, seem to be a pretty good predictive tool, at least for the larger scale gravity waves that we see. So let me turn finally now to what we saw from the ground on the day when we thought the forcing was too weak to give us an interesting response. This is, again, a kilogram. This is made from the Lauder imager that was on the ground in the lee of the Southern Alps. This is an east-west direction. West is on this side, east is on this side. And so basically this plot is composed of an east-west pixel row across the center of that imager that we scan in time. And so this is an east-west time cross-section. And you see here that there's a lot of wave activity with apparently relatively rapid phase velocities. When phase structures are more nearly horizontal here, that indicates that that wave is likely to be a mountain wave that has almost a zero east-west phase velocity. And there's a significant interval here where we have very large amplitude responses. In fact, you can discern what looks like a sawtooth pattern here. Different phases of the wave go from very hot to very cold, suddenly back from cold to hot, and then a long linear ramp from hot to cold again. So it looks very much like a wave that is physically overturning. And we're looking vertically, and we're seeing slow temperature changes until we get to the overturning portion. And then all of a sudden, we go from very cold, which is high, to very hot, which is low. And this wave is slanted up into the west, as you'd expect. So this is an animation of that movie, an animation of that sequence. And I couldn't get a shortened version of this movie, so you'll have to bear with me. So this starts several hours before that interesting event occurs. And what you see here is a lot of small-scale, relatively incoherent structure that seems to be propagating in all kinds of different directions. Again, this is a 180-kilometer east-west field of view, 144-kilometer north-south field of view. And you see some coherent structures and some motion, but not much that is stationary until we get up to about this time. So here is the sawtooth pattern I talked about. You can see very clear phase structures here that are moving very little with time. The wavelength is changing, and that's probably the dominant cause for the motion of these phase structures. But you see this very clear tendency for a really hot region, which has to be very low, moving more or less linearly toward a quite cold region, which has to be very high, and then suddenly back from that cold high region to a warm low region. So it's as if I'm looking up at this overturning wave structure. And what is really interesting here is something we had not expected to see. There are also lots of very, very short components in the stationary wave field. So this particular forcing seems to excite not just these larger scale 60 to 80 kilometer horizontal structures, but also 10 to 15 kilometer horizontal wavelengths that also contribute very meaningfully to the momentum flux into the mesosphere. So this is a series of snapshots of this event. And again, you can see this event building with time. So in this region, it's probably from maybe 11:30 to 12, it's probably most intense, a strong sawtooth pattern. And as it dies away at larger scales, smaller scale features within that field still emerge. And so we can easily diagnose the different parts of this field at large and small scales and ask, which components contribute most to the momentum flux throughout that evolution. And it's interesting that during this interval, when we saw that very large response, we also saw, using the FPI that was at Mount John, FPI is the Fabry-Perot interferometer that measures both winds and temperatures at these two airglow layers. And it showed a significant enhancement, presumably because of the background wave environment, exactly during the interval over which we saw that strong mountain wave response. Up until then, we did not see significant mountain wave activity, and it persisted at much weaker amplitudes thereafter. So we were able to use these velocities and infer the wave parameters. Steve Smith, who has the imager at Mount John, was able to look at the differential position of the horizontal phases in his imagers at these different airglow layers and for a vertical structure. And so we were also able to make an estimate of the momentum fluxes for these cases. For reference, this is an AIRS image at 41 kilometers, so 45 kilometers lower in the atmosphere, but it shows a very similar phase alignment and horizontal wavelength as we see in the airglow layer. And this is at 9 hours earlier, so it's unclear whether this was really representative of the wave environment, but these are the ECMWF forecasts in the vertical velocity field at 41 kilometers at 02 UT, which corresponds to the AIRS time, and at 11 UT, which corresponds to our observation time. And it suggests that that same wave field was present at 42 kilometers throughout this event. So this was a long-standing wave event at 41 kilometers, but we only saw a portion sneaking through when the upper atmosphere wind structure was conducive to the wave having large enough vertical wavelengths to get to those higher altitudes. So again, momentum fluxes for this case now have to take into account this averaging factor because of the tendency for the averaging over the OH layer to reduce the apparent perturbation of the wave in the temperature field. And again, we see relatively large values. So once again, we see a case where weak forcing gives you very strong responses, and another example of a real hotspot in terms of a hotspot for forcing at higher altitudes. The one thing that, the EC forecasts, well, they don't go to 80, they don't go above 80 kilometers. They have a sponge layer above about 60. So you can probably believe their mean wind and temperature structures to higher altitudes, but I would not believe their amplitudes to higher altitudes. And even at lower altitudes, they do not seem to get the amplitudes right, even though they do pretty well with the phase structures. So, summary. There are lots of sources that seem to yield gravity waves that very happily get to very high altitudes in the deep wave environment. Mountain waves in particular exhibit a very wide range of scales, orientations that do not have as much to do with the terrain as with the orientation of the wind, and quite a large number of responses at high altitudes. These smaller scale mountain waves, as little as 10 kilometers and as much as 100 or more, very readily get to the MLT under suitable propagation conditions, and they appear to dominate the momentum fluxes that we see at those higher altitudes. The local momentum fluxes can be 10 or 100 times as big as the mean, suggesting that if these hotspot events are very frequent, they should really dominate the mean statistics. And then trailing waves readily occur, but they typically occur at somewhat larger spatial scales, and they refract into the polar jet as they propagate away from land. Done. I'm sorry. I should have started off with that. Mesosphere and lower thermosphere. It's the region from about 60 to 100 or 110 kilometers. So should I go back and start over? Yes. What is really interesting, and we've seen this in a number of cases, not just in these deep wave observations, is that the larger scale environment can oftentimes modulate the smaller scale responses at the higher altitudes. It's as if the large scale wave modulates the wind and temperature field and either prevents the smaller scale waves from getting through, reflects them or absorbs them, or enables them a propagation channel that might be very brief. And one of the big revelations, I think, in addition to the science, is the potential for these high-resolution global models to do a remarkably good job in anticipating the wave structures, if not their amplitudes. And once again, thanks to our team of researchers, and especially the NCAR EOL support staff for all their help. Thanks.
For Dave?
Dave, can give us an idea of how this contributes or compares to the global gravity wave budget as it reaches the upper mesosphere?
Well, I have my...
Just in the southern area where you have all the... This is the middle of winter. You have all of these storms crossing the ocean, and then you have these little hot spots. Are they really driving the global budget? Or
well, I think that depends. The answer depends upon who you ask the question of, I guess. I have my biases, and I think that these small-scale intermittent events that can demonstrably become really, really large have the potential to make a very large statistical contribution to the mean. I'd be very surprised if they didn't. I'd be surprised if these regions of local strong drag on the mean flow at higher altitudes don't project to larger scale motions very readily, because every time you have a localized drag, you have to have a large scale response to it. You have to generate other waves, and you have to have a differential zonal mean flow with latitude than you had otherwise. You know, there are other waves that can contribute. We chose a hot spot especially because if you want to have confidence in your interpretations, it's a lot easier to do that where you have lots of signal noise and big amplitudes. But again, you know, the focus on hotspots will or can only emphasize the potential role they play in the average larger scale circulation, I think. I mean, I think the potential is for these small scale waves to play very significant roles, but we really need to do the modeling study with a model that can resolve the large and small scale waves in order to try to look at the balance.
Make a big difference for hemispherical asymmetries. Is this really a southern hemisphere winter thing?
Well, there are hot spots in the northern hemisphere as well. It's just that, well, Rolando would know this better than I, but I think that the models don't have as difficult a time getting the northern hemisphere vortex structure and temperature correct. They have a much more difficult time at southern latitudes. And it might be that the hot spots in the southern hemisphere preferentially excite more small-scale waves that can't be accommodated directly.
I assume if there's no turbulence, the model can do a good job. I'm not too surprised. But if you see a wave breaking, for example, at a wave critical level, how does a model perform in that region?
Oh, you mean the global models?
Yeah.
Well, the global models probably are pretty gooey at the smallest scales. You know, they may capture the heating that is induced, but they certainly can't resolve any of the small scale. They can't resolve the instabilities. Rolando, is it mostly a radiative damping at smaller scales? If I use the ECMWF models or the WRF models to try to capture the dynamics accompanying wave breaking and instability in the stratosphere. Right. Right. Right, but if it has local dissipation of the wave in that area, then it also has the potential to still excite secondary waves as if the wave breaking was more completely resolved, I think. Well, I mean, if you look at the WRF simulations of the wave breaking that I showed here, it showed arising from this region of wave breaking, waves propagating both upstream and downstream. You know. Yeah, that's right. Oh, no, I don't think so. They are doing some simulations at 2-kilometer resolution, but these were at 6, I believe. And even at 2, I don't think you're resolving the structures. Yeah. Well, no, but there are two types of secondary wave generation. One arises from the detailed nonlinear interactions at smaller scales within the parent wave. The other one arises as a packet scale response. Because if I have the momentum that accompanies a packet adjusts the mean flow, and that radiates waves on the packet scale. And so that's something that you don't need to resolve the wave breaking dynamics to capture. But it's the smaller scale features that lead to smaller scale responses that you would like to resolve to be confident of those dynamics. And they're not doing that for sure.
Yeah, I'm willing to accept that. I mean, you know, this is something that we have in our models. They don't begin to approach it. But what people do in the models such as CWF, they have the work more completely clear to me. Once you get to the point that you cannot resolve the actual turnover.
I think it makes sense for the large-scale models to get the linear dynamics pretty well right, even if they get the amplitudes wrong. I think it's just dumb luck that they get the small-scale dynamics right when they're not resolving the fundamental small-scale structures. Yeah.
The intensity of the forcing depends on the bottom topography, right? But
that's what we assumed, yeah.
Yes, but also the scale of the forcing depends on the bottom topography. So is there any relation between the size of the structure you observe and the forcing scale?
That's a really good question. Because you can imagine that if you've got really small amplitude, low-level flow, the air is going to find a different way over or around the terrain than it will if it has lots of kinetic energy and it just blasts up over the terrain. And so there's the potential for different effective forcing levels in that case. And if you imagine that different forcing levels expose the flow to different scales of topography, that could account for some of the different scales we see at higher altitudes. I mean, I'm not sure that makes any sense, but it was surprising to me. You know, we've all been trained that if you have some sort of a mountain barrier and it's a linear, you're going to get a wave that's aligned with the barrier independent of the incident flow. It's just going to have different cross-stream velocity. But that's not the case in New Zealand, where I have complex terrain. In almost all cases, the dominant phase structures in the responses at higher altitudes were more or less orthogonal to the incoming flow. When the flow was cross-mountain, the dominant phase structures were aligned with the mountain spine. When the flow was mostly east-west, as in RF-22 when we had that 240-kilometer, mostly north-south response that was actually tilted a little bit more counterclockwise, you have a response that's, again, normal to the flow but not to the terrain. And when I have flow that's along the islands rather than across the islands, the flow changes, the orientation changes 90 degrees. So it seems to have more to do with the incident flow than with the prescribed terrain that's assumed to be 2D.
There are cases in which, when, for example, the high-crowd fly over the small highlands, so the forcing is very localized, and also the size of the forcing is very well defined. I mean, you don't have a complex. So in that case, what do you observe?
Well, but there's no dominant alignment there because that's a ship wave pattern. That gives you waves that very quickly begin to refract, and it gives you this ship wave pattern that we saw clearly in the air glow responses at higher altitudes. That's predicted by the Fourier array models as well. They can do a good job with that.
I have another question related to that. I'm still puzzled by the negative flux, so I was wondering whether you have access with those measurements to the fluxes in the Fourier space, where you can, because this is an average flux.
Yes.
So it's average over the time, as we say, but it's also average over the wave vectors. So it's an integral of the spectral flux.
Yes.
But I think it's remarkable that you get a negative flux, and that can be related to the fact that...
well, if it's wrong, it's not mine, okay?
I don't think it's wrong. No, I was actually thinking the other way around. I mean, as you said, in the model, things at large scales tend to be linear, but indeed, I mean, the geophysical flows are non-linear systems.
That's right, yes.
And the measurements is the real thing. So you can capture with measurements something that you could not have captured with the model. So, and when you get the negative flux, it looks very much to me like an inverse cascade, an inverse energy.
It could easily be.
Inverse energy flux, which is typical of 2D systems and nonlinear 2D systems. So it will be really interesting if you could use those measurements to compute the flux, not only averaged over time and over the wave vectors, but
As a function of wave number.
Right.
Yes.
Because that will tell you whether you have an actual inverse cascading.
I totally agree. I totally agree. Yes.
And if you find that this flux is constant over the over a band of wave vectors, then you would have proved that that probably they push too much the parameterization, and the system should take into the models should take more into account the nonlinearities which allow for an inverse energy cascade, for example.
So a couple of comments. First of all, it's not clear to me that the Whorf model that gave positive fluxes everywhere is capturing all the nonlinear dynamics that could potentially give you negative fluxes on occasion. And Ron has a lot of experience calculating energy fluxes from previous campaigns. I have no reason to believe that that's not done right, especially because he says he can get the same answer from the W prime P prime covariance and inferred from the U prime W prime covariance using the Eliason-Pulm relations. But I still have an interest, as you, in looking at the finer scales within that, and not just as a segment average value, because I don't think that tells you very much.
So you have measurements to compute the spectral flux.
In fact, we will have 25 hertz data.
Okay.
For all those parameters. So far, Ron and my group have only used 1 hertz data. The 25 hertz data will allow us to do the spectral calculations and the spectral discrimination of the contributions to the momentum flux and the energy flux and the wave flux and the turbulence flux.
So you can do like the composition of the energy flux in waves and vortices?
There's no reason why you can't do that. That's right. I think you can do that easily. You just Fourier decompose it, you do the covariance in Fourier space, and you're done.
So because I don't quite have an idea of how those measurements are taken, but so you have access to the point-wise value of the velocity field. You actually have you can have a 3D matrix of the velocity field over those.
Yes.
Okay.
The GUS probe on the GV has an absolute altitude knowledge of 20 centimeters. And it can get you vertical velocities at better than, substantially better than a meter per second. And the horizontal, all three components of velocity at much better than a meter per second. So, and because it's flying at about 250 meters per second at 25 hertz, you have 10-meter sampling, basically. And that's surely not a wave response. That's a turbulence response. So at the highest frequencies, if the velocities are not biased, you have the potential to look for the turbulence fluxes, and then at larger scales, the gravity wave fluxes.
Yeah, that would be interesting. Okay.
So we're just getting started.
Thank you very much.
More questions for Dave? If not, thanks
Thanks,
again.